Yesterday, the topic of differential equations came up when we were talking about power series. And so since the topic of differential equations has come up, we should talk a little bit about differential equations. Now, this is a major topic. You're going to um, you're going to take an introductory course in differential equations. We have one here at Skyline called Ordinary Differential Equations. Then, as an upper division student, you'll take probably a series of courses, or is it a sequence of courses? Well, the knowledge does kind of add up. So you'll take a series of courses in ordinary differential equations, then a series of courses in partial differential equations, and then probably also study systems of differential equations. What I'm saying is differential equations is a big thing. Differential equations is one of the major ways we take the math that we know and make it interact with the world. All right. It's very much not like applications that we have in algebra. Those are the applications that you get in like algebra class. Those are very much contrived so that you can do an algebra thing right there. So a differential equation is an equation involving the derivative of some unknown function. That is to say, the solution to the equation is a function. The solution to the equation is a function. So we've already done some differential equations. Every time I ask you to find an antiderivative or an indefinite integral, I'm asking you to solve a differential equation. So we've seen this a lot. Note. We've already solved some differential equations. Oops. We've already solved many differential equations. We just didn't frame it in the context of differential equations. So for example, all those antiderivatives. So I would say something like find the indefinite integral of, let's say, x sine x squared to x. And then you would go and do some kind of substitution thing here. So the derivative of cosine is negative sine. So negative, and then I'll need a 1/2 from the x squared cosine of x squared plus c. So earlier I had asked you to find the antiderivative or the indefinite integral of x sine x squared. We can also frame this same question as a differential equation. We usually don't, but we could. So this could be also framed as a differential equation that says dy dx is equal to x sine x squared. So asking you to find an indefinite integral is asking you to solve a differential equation. In the second one, we would say, well, since the derivative is x sine x squared, that means y is equal to negative 1/2 cosine x squared plus c. Same question, same mechanic, but a different context. just a different way of asking the question. It's not so much a new idea, just adding to an old idea, which is just what math is all about. Take the old ideas and add to the new ones. All that algebra that you did is just arithmetic in a new context. So another time another place we've seen a differential equation, acceleration due to gravity is constant. With the usual context, acceleration due to gravity, as long as we're staying pretty close to the surface of the Earth, acceleration due to gravity is constant. Here's an example of a differential equation. We make this observation, acceleration due to gravity is constant. And we can frame this as a differential equation. Acceleration is the second derivative. Since we're talking about gravity, I'm just going to call this the second derivative of the change in the height. So acceleration is the rate of change of the velocity and velocity is the rate of change. So that's the derivative of the velocity. With respect to time. And velocity is the rate of change of height with respect to time when stuff just be falling. So the rate of change of position, the velocity is just the rate of change of position, that is the derivative with respect to time. So if I call position my function, then the acceleration is just the second derivative. So we're saying the second derivative is constant. So when we say acceleration due to gravity is constant, we're saying the second derivative is constant. And if we want to say the second derivative is constant in equations, that's right here. We say the second derivative is some constant. So we're setting up an equation involving the second derivative of the position. We usually don't frame this in terms of differential equations. I think actually this book does frame things in terms of differential equations. Can't remember where this shows up in this book. I should probably know that. I've been teaching out of this book for so long. I should read it at some point. So we do the same thing that we did before. We just do it twice. We find an antiderivative. So if y double prime is k, then y prime is k. I'm going to use t for time, plus some constant. I'm going to stop pretending, and I'm just going to say we all know that the constants here is the initial velocity. And then we can integrate again to solve for y. So v naught is your initial velocity at time 0. If you don't want time to be 0, just subtract it from the t. If you want to start everything at 3 and you have the velocity at 3, just put t minus 3 in the parentheses and put that for your velocity. So it's initial enough. Where time happens is where we decide it happens. Where time starts is where we decide it starts. S naught is the initial position. So here's what we want to observe with these two examples. First of all, this is not something new. We've done this before. We're just going to be framing it in terms of differential equations. This second example is important because we've taken something that we've observed. We were there. We've taken something that we've observed. When we watch how things fall, we observe that the acceleration is constant. They speed up, but they speed up at a constant rate. And so we need to quantify that by describing it with functions and equations. And then we need to build machinery like calculus and antiderivatives to be able to find out what the position function should look like. Now there are certain things we have to keep in mind. We know that acceleration due to gravity is constant so long as we stay close to the surface of the Earth. We go too far away from Earth, then all of a sudden gravity isn't so constant anymore. Gravity starts getting weaker. But this is just us saying, let's keep things simple. It's like when in physics, when you decide that you're going to ignore air resistance. That just means you're going to have your projectiles going a little bit slower. You're not going to throw them at major league speeds. You're going to throw them a little bit slower so that the air resistance is negligible. Or when you say that you're going to ignore friction. I always get amused when people joke like, oh, we'll ignore friction and ignore air resistance. And students, computers, you're not computers. Except the one robot that's been sent from the future. I know who you are, by the way. So, students jokes like, oh, well, what if we don't ignore air resistance? What if we don't ignore friction? It's like, okay, yeah, let's make the problem more complicated. Let's start with the more complicated problem. Is that what you want? Is it? Is it really? Then how about we do the simpler problem first? I don't know. When people complain about frictionless vacuums and stuff like that, I think they're being a little bit silly. I hope they recognize that they're being silly. But anyway. So we could be like, well, acceleration due to gravity isn't constant. If we drop things from, like a far way away. It's like, oh, great. Okay, instead of the gravity being constant, I'll make it the inverse square function. And then let everybody get lost. You know what I'm talking about? Anyway. So here's what we want to observe. The order of a differential equation is the highest order derivative that's present in the equation. So this is a first order equation. dy dx equals x sine x squared is a first order equation. This equation, y double prime is equal to some constant, acceleration is constant, is a second order equation. So the order of a differential equation is the highest order derivative. That's present in the equation. So our acceleration example is a second order differential equation. There's a lot more classifications to this, but we'll just start with that one. Second order differential equation. It's also an ordinary differential equation because it involves ordinary derivatives because y is a function of one variable. It's also a linear differential equation because y double prime is to the first power. All the derivatives and functions are to the first power. So there's all kinds of ways we classify things. Dy dx up here equals x sine x squared is a first order equation. So that would be a first order ordinary differential equation. The class that you'll be taking here, if you take the differential equations class here at Skyline, or pretty much most places you take it, will be ODE, ordinary differential equations. Then later on, you'll take a bunch of classes in PDE, partial differential equations. So notice that when we had a first order equation, we ended up with one arbitrary constant. When we had a second order equation, we ended up with two arbitrary constants. One corresponding to the initial velocity and one corresponding to the initial position. The first problem was just completely out of context, so it's just one arbitrary constant, that constant of integration, because we integrated one time. In the second one, we had two arbitrary constants, we integrated two times. So what we're doing when what we want to note is that a differential equation defines a family of functions with some arbitrary constants. A differential equation defines a family of functions. And this is getting at the nature of solutions to differential equations. A differential equation describes a family of functions. So when I talk about a family of functions, all these functions are going to be related. That's the family parts. And what we saw when we were doing our indefinite integrals is that we had some constants. So all the functions, all the antiderivatives, were only different from each other by the constant at the end. So they were all vertical shifts of each other. Just one to the other is a vertical shift. That plus c just moves things up or down. The plus c produces vertical shifts. So the plus c produces a vertical shift. And all the solutions to dy dx equals x sine x squared, all the solutions are just going to be 1/2 cosine of x squared moved up or down. So they all have the same shape. They're just vertical shifts of each other. all the solutions to y double prime equals some constant are going to look like parabolas. Just going to be moved up and down and right and left. So the plus c produces a vertical shift. So for example, when dy dx was equal to x sine of x squared, that told us that y should look like a negative 1/2 cosine of x squared plus c. All the solutions had this shape, but we had a plus c attached to it. So they are vertical shifts of each other. All the solutions to the differential equation are vertical shifts of one another. So we can figure out a particular solution if we have information that will tell us the plus c. An additional piece of information is required to figure out what the plus c is. We would refer to this, the minus 1/2 cosine x squared plus c, we could refer to this as the general solution, in the same way that we refer to it as the general antiderivative back when we were learning antiderivatives. So we refer to this as the general solution. If we have an additional piece of information, an initial condition, then we can turn our general solution into a particular solution by solving for plus c. If we have an initial condition, then we can find a particular solution. We solve for plus c. So for example, if we were given the information that dy dx is equal to x sine x squared, and that y of 0 is equal to 5, we're given a differential equation that defines a family of solutions, and we're given an initial condition that will pick one member from that family. So the differential equation defines a family of solutions. The initial condition picks out one member of that family. A differential equation paired with an initial condition is referred to as an initial value problem. So a diff EQ plus an initial condition is an initial value problem. So the differential equation gives us a family of solutions. So this tells us that y is minus 1/2 cosine of x squared plus some constant. The initial condition allows us to figure out what this constant is. So here's our general solution. And then if y of 0 is equal to 5, I can plug in the 0. Negative 1/2 cosine of 0 squared plus some constant is equal to 5. This will allow us to solve for c. So this tells us that c is equal to 5.5. So the particular solution that we're looking for is negative 1/2 times the cosine of x squared plus 5.5. It's just like clue. The differential equation is just the list, it defines the family of solutions, the family of suspects. So this would be like the Colonel Mustard, Miss Scarlet, and I can't name all the rest of them. Then all the clues is the initial condition that allows us to pick which member of that family, I know they're not all related, but that family is the murderer of Mr. Body. That's the victim's name, right? Mr. Body. Can't remember that thing about Clue. There's also variations on Clue now, where there's different sets of suspects for particular fandoms. So, all right. So notice that in the acceleration problem, we had two arbitrary constants. So we'd have to have two initial conditions. So to make a complete problem, we could say y double prime, the second derivative is equal to negative 32. I'm going to go old school. And I'm going to use feet per second squared. This is a second order equation, so I'm going to need two initial conditions. Usually, we'll say something like v naught, the initial velocity is 88 feet per second, and the initial height is 15 feet. So here is an initial condition problem, or initial value problem. I have a differential equation, which will give us the general solution. It's second order. It will have two arbitrary constants. Then the initial conditions, we need two of them because there are two arbitrary constants. So the differential equation defines the general solution, and it will have two initial conditions, or with two arbitrary constants. Since there are going to be two arbitrary constants, we need two initial conditions to find those constants. And that makes a complete problem. Now we'll get it down to one particular solution. We like this one because it's easy to solve, because we know where v naught and s naught go. This will just tell us that y is equal to negative 16t squared plus 88t plus 15. So where before we just had the differential equation gave us the function with the two arbitrary constants v naught and s naught, here we have initial conditions so we can find a particular parabola. I wrote v naught and s naught, but we can write them as initial conditions by saying y prime at 0 is equal to 88, and this would be that y of 0 is equal to 15. In this case, we had two initial conditions, the initial position and the initial velocity. All we need is two pieces of information about the function, y. So if I had, we could also have like a boundary value problem. If I told you that y of 0 is equal to 15, and then y of 5 is equal to whatever the height is there, then we'd still be able to find our particular solution. We just need two additional pieces of information about the function. All right, so tomorrow I want to talk a little bit more about building some differential equations. They come from just observations that we make that involve rates of change. It's just how we describe things. The one that we solved yesterday, y prime is equal to some constant times y, we can frame that in terms of population by saying the rate of change of a population is proportional to the size of the population. That was the differential equation that we were looking at yesterday. The rate of change of the population, y prime, is proportional to the size of the population, equals a constant times y, which was the size of the population. And this makes sense because the bigger the population is, the faster it will grow. If you have 10 rabbits, they will grow at a certain rate. But if you have 20 rabbits, they're going to be growing, your population of rabbits is going to be growing twice as much. If you have 100 rabbits, it will be growing 10 times as much as your 10 rabbit population. Now, there's things that slow that down. Human populations slow down after a while as we start competing for resources. So we'd have to have a big field of carrots for those 100 rabbits so that the rabbits just continue to make more rabbits. That's kind of your rabbit defense mechanism. Wolves are like, oh, well, we'll make you be able to work together really well, and we'll give you sharp teeth and claws and speed and all that kind of stuff. And the wolves are like, oh, sweet. Then alligators are like, oh, you get to hide in the water, and when you clamp down on something, it just like crushes stuff. So you're going to be really good at that. And alligators are like, oh, sweet. And then rabbits are like, well, awesome. What's our defense? And it's just like, oh, well, there's going to be lots of you. And the rabbit's like, oh, hang on, what? You're going to eat plants, but your defense is there's lots of you. So get started. Anyway, what are we talking about? Oh, yeah, rabbit populations. So the order of the differential equation is going to tell us how many arbitrary constants that are going to show up in the process of solving. And then we're going to learn a couple of techniques for solving differential equation. And then I'm going to be like, well, in general, we're not going to be able to solve our differential equations. We're going to have to approximate them, depending on how complicated they are. We learned to solve some famous ones, but just like factoring, it kind of gives us this false idea that there's a hand technique for all these differential equations, and we just have to figure out which one it is. And there's just not. We can get better, more accurate solutions just by having our computers use a lot of computing power to create a model. It's like kind of the modern math class is just like I'll throw computing power at it. Just like there's a lot of problems that can be solved just by throwing money at them. You know what I mean? People like to say that money can't buy happiness, but those are people with big piles of money that don't have to worry about, like, shelter and food. When you have to worry about shelter and food, money can literally buy your happiness. That's right. That's a line fed to you by the man to try to convince you that you don't need money. And then those same people build a society wherein you need, wait for it, money to live. So I'm not necessarily advocating for the abolition of said system, but we all need to be realistic about how said system works. Because a lot of times I'm like, oh, yeah, this system where we let people just steal all of our money, I don't know if that's a good system. Then all of a sudden, oh, what are you, some kind of communist? And I'm like, well, maybe I am, but maybe you should get over your propaganda and realize that it's not the system of government or the system of your economic system, but corruption that is the problem. And any system of government is going to find corruption. I mean, seriously, people, is this that hard? How badly are we going to let all that propaganda in the 80s infect us? You know what I'm talking about? Anyway, I graduated high school in 1989, so I was in the thick of it. I know a lot of you, this is like probably like 10 to 15 years before y'all were born when I was in high school. But if you were in the 80s, in the late 80s, in the 80s in general, if you were good at math and science, you were pushed into engineering because we wanted to create as many engineers as we could, because I guess we needed to build even more missiles, to have more missiles than the Russians or the Soviets at the time. You know what I mean? So, oh well. And it's kind of ridiculous because it became a money fight, and the United States at the time really could not lose a money fight anywhere in the world. Oh well, what are you gonna do? I'm from the government and I'm here to help. Well, okay, so the statement "I'm from the government and I'm here to help" is in fact true, but they're just not here to help you. That's as long as we keep that in mind. I'm from the government and I'm here to help. Jeff Bezos. I'm from the government and I'm here to help. Bill Gates. So as long as you can have enough money to buy the help, then yeah, they're here to help. But I don't think they're here to help anybody here in the room. You know what I'm talking about? Anyway, that's going to do it for today. Tomorrow we'll talk more about where differential equations come from. And then we'll learn some of the easier techniques for solving differential equations, the ones that work. Just because most differential equations aren't solved by some by hand technique doesn't mean there's not use in learning those techniques. Those are still skills that we need to have. It's kind of like the figures in figure skating. That's where the figures come from. I know a lot of people aren't, that might be a little bit too niche of a fandom to go for figure skating. I don't know if you know this, but it used to not just be the performance aspect. You used to actually have to go and skate figures. There was like a technical portion. You had to go out and make a circle. And then you had to make a figure eight or something like that. You actually had to skate. That's where the figure comes from, I think. I could be wrong about that, but I know they used to have like that technical thing. Compulsory, thank you. You had to demonstrate basic competency at some things. You couldn't just wow people with your quadruple axle and stuff like that. You know what I'm talking about? I'm glad some people are familiar with figure skating. Usually I start bringing up figure skating and there's like a room full of 40 people that are going, what is he talking about? What's figure skating? That Olympic sport that we watch like once every 4 years. Anyway. All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day and thanks for playing.